Grasp on Robotics seminar. We have Dr. David Held here today. I'm Dinesh. I'm faculty here at Penn, and I'm the host for this talk. And really glad to be able to welcome David. As a quick reminder, before I formally introduce David, previously recorded talks can be found on our YouTube channel and on the website. And you will have an opportunity at the end of the talk to provide your questions. And if you have a question during the talk, then please raise your hand and I'll bring a microphone over to you. All right, so David is an associate professor at CMU, and he runs a lab that's called the RPAD Lab, Robots Perceiving and Doing. And he works at the intersections broadly of robotics, machine learning, and computer vision. Over the years, I've really admired how David's work has kind of spanned a lot of the robotics stack. I remember first as a PhD student noticing when David also was a PhD student with Silvio and with Silvio Savarese and with Sebastian Thrun at Stanford, this really cool paper that was very influential then on tracking and doing tracking in video at over like 40 or 50 FPS or something, at 100 FPS. Yes, yeah, I should remember that number. And then that was really influential at the time. It was very seminal. But then during his postdoc as well, David has this really cool line of work. He did his postdoc at Berkeley with Peter Robeel and had this really cool line of work that I find myself coming back to over the years several times, this reverse curriculum generation stuff. It was a really cool idea at the time, and I was really influenced by it, as was a lot of the field. And in recent years, David has really been leading the line on deformable object manipulation, articulated object, soft deformable articulated object modeling and manipulation. And today, David will speak about kind of generalizable and precise robot manipulation. I'm really looking forward to hearing it. Please join me in welcoming David once more. And David, whenever you're ready, you can start.
Great. Well, thanks so much for the kind introduction. Thanks to everyone for coming. I'm David Held. I'd like to tell you about some of the things I've been working on lately on this topic of precise and generalizable robot manipulation. So as a background, I guess many roboticists, probably many of you all, would like robots to one day work in our homes, cook food, do flexible manufacturing, adapt to new manufacturing tasks, work in agriculture, and many other complex settings. Now, if you look in social media or online, you can find many videos that look like this of robots doing super impressive acrobatics. And it makes it look like robotics is basically solved in some sense. And you can actually buy one of these robots. And here's a video of someone who bought the robot. And look, it's already standing up and doing super cool things. That's awesome. Here's another video you can find online of a robot cooking. This is an autonomous robot from Stanford University, the Mobile Aloha paper. That's great. You can buy one of these robots as well. And but you can't actually find very many videos of the robot that you buy off the shelf, put in your kitchen, and it starts cooking for you. It doesn't really work that way. So why not? Where is my robot chef? So let's think about what the problem is with current approaches to robot learning. The most common approach to robot learning today is to take a large-scale robot data set, such as Droid or many other ones, input that data into a vision language model that you can fine-tune with this robotics data. You can also add in some prior world knowledge about captioning images or things like that, and have the model output actions. And here's an example of the robot doing a task. The task was to move the Coke can to Taylor Swift. This is from the RT2 paper from Google DeepMind. And if you watch this video, one thing you might notice is that it correctly identified which of these three pictures was Taylor Swift. Great, that's a very important thing for robots. Taylor Swift is amazing. We all love her. But you might notice from the manipulation side, the Coke can was actually very poorly placed on the picture of Taylor Swift. It basically dropped the Coke can kind of nearish to the picture. So, and you can see many other kind of examples of robots kind of roughly getting a sense of what they're supposed to do, but not actually doing it correctly or very precisely. So yeah, so a lot of robot learning research today is really has been pushing on this axis of generality. How can we make robots that can really understand everything in the world and have general world knowledge? And we've actually made a lot of success on that. Robots know who Taylor Swift is. But on another axis, precision, maybe we have not been able to get these foundation models to work in a very precise manner. And so on the other hand, we have specialist models, task-specific models that have been trained and designed to only do one particular task. They can't do everything, but they can do one particular task well, like grasping. There's lots of models that are very good at grasping objects, and they're not very general. So what we eventually want is models that can do both. Models that are general enough to understand Taylor Swift and every other thing in the world in a very general sense, and can do all your household chores. But we want them to have the precision of these specialist models that today can only do one thing. So how do we achieve both precision and generality? So we can look at the insights from both of these models and see what we can extract from that. So from all the recent research in foundation models, we've learned that we want our models to be trained with large-scale data sets, expressive policies, and limited assumptions. And if you do those things, then you get lots of generality. Now, what insights do we get from specialist models that we can extract to figure out how to also obtain high precision? So let's kind of dig into that. So one example of a specialist model that I really like in particular is this paper called Content GraspNet. The goal is to output 60 grasping poses for all the objects in the scene. So basically, it takes as input a depth image or a point cloud and outputs for every point in the scene how you would grasp that point. And once they've output all these grasps, they select one of them and then do motion planning to figure out how to move the robot to be able to grasp the object. So you can sort of think about this in some sense as a kind of motion hierarchy. At the high level, the robot is doing scene level reasoning and predicting where should the gripper go next to achieve this task. In this case, the next location would be some target grasp pose. And then a low-level policy is used to figure out how to move the robot to that place and do the grasping. In this case, the low-level policy is basically just motion planning inverse kinematics, but you could imagine using a learned policy for this part if it were needed to do so. So the main insight here is something that I think of as a motion hierarchy, basically outputting at the high level a grasping pose, and then the robot at a lower level figures out how to move to that pose. And so the question that I would like to ask is, how can we take this insight to a more general set of tasks? So I call that hierarchical motion policies, and I've applied it to a few different robotics problems that I can tell you about today. Cool. Okay, so I'm going to start with this project on articulated object manipulation. The goal here is to enable a robot to manipulate any articulated objects. So doors, drawers, cabinets, microwaves, ovens, things like that. This is a project led by my PhD student Yufei Wang, who is currently on the faculty job market, as well as Ziyu Wang, who interned with us. So how do we get a robot to be able to manipulate all these articulated objects? The first step is we need some data to train on. And so we generate that data in simulation. We do it with a fairly heuristic procedure. We sample a number of grasps around the handle of the object. We do motion planning to reach the handle. And then we use kinematics of the object to generate the opening action. Now, not all of the demonstrations are successful. Some of the grasps will fail, but it's in simulation. We just want a big data set. So we filter out the demonstrations that don't work. We keep the ones that do. And that enables us to generate a data set that can of how a robot could open all of these different kinds of articulated objects. Now, because we're in simulation, we have the advantage that we can randomize pretty much anything. So we have a number of different objects that we're randomizing over. We can randomize over the initial configuration of the robot relative to the object, and we can randomize the camera pose. And through this procedure, we end up with a data set of over 40,000 trajectories and almost 5 million observation action pairs. Great. Okay, so now we have our big articulated object manipulation data set. Next step is let's train a policy. So we start off with kind of the standard thing. We put in the observations to a big neural network. It's a 3D diffusion policy. It's supposed to output delta end-effector poses. We train it on the 40,000 trajectories that we've collected. And here on the x-axis is the number of training objects. And the y-axis is the performance on unseen objects. And here you can see the performance of these end-to-end policies. So basically, they're not working. And even as we increase the number of objects that we train on, it still is not able to learn how to generalize to unseen objects in unseen configurations. So this is might be surprising to some people who believe that end-to-end policy learning is the way to go, and all we really need is more data, because in this case, we have lots of data. We generated 40,000 trajectories in simulation. We could generate more if needed, but the curve doesn't really seem to be going up. Yeah. On the seen objects, yeah, that's a good question. I don't actually know the answer to that question, but I believe it to be pretty high. But I'll try to. I should do that. I agree. Yeah. Any other questions at this point? Yeah. Yeah, that's a great question. Why is it the case? I would say potentially a couple of things. So one is that our task requires a reasonable high amount of precision. You have to grasp a handle and pull it out in a precise direction. So this isn't just a simple kind of pick and place task of putting an apple into a basket or something like that. Like it's a little bit harder than some manipulation tasks, and we're also really testing the limits of generalization. So trying to not just collecting teleoperation demonstrations in your environment and testing on the same objects, but seeing how much it can generalize to unseen articulated objects. So yeah, I guess that's kind of the answer that I have. But yeah, I guess it is interesting that it does seem somewhat counter to at least the general vibe that many robot learning people have that this should work, I guess. Oh, okay, cool. Great. All right, so that didn't work. So we played with a lot of different ideas to try to get it to work. The idea that we ended up with that led to this actually working is something that we call hierarchical imitation learning. So here's a demonstration, and here are some of the frames in the demonstration. So we have we train a high-level policy to predict the robot pose at a couple of keyframes. In this case, we define the keyframes as the frame where the robot grasps the object, the handle, and then the frame where it's fully open, so just 2 keyframes. And then we learn a low-level policy to figure out how to interpolate between those keyframes. So to kind of break this down, so we're going to take in our point cloud observation, input to a high-level policy that will output some high-level information, and then that high-level information, along with the original observation, both get input to the low-level policy that will output the robot actions. The high-level information in this case is just the gripper pose at the keyframes, which we represent as 4 points on the gripper that we're going to try to predict. And so you can kind of think about this as the high level is telling the robot where to go. The low level is telling a robot how to actually move there, meaning what is the circular arc that you would have to follow to open a articulated object with a rotational joint. Both the high level and low level are trained with behavior cloning to imitate the expert. So the low level is not trained specifically to try to reach the high level prediction. It's just trained to imitate the expert the way a normal imitation learning policy would be trained. The only difference is that we have this extra input to the low level from the high level prediction. Okay, so in terms of our architecture, the high level has a particular design that we found to work pretty well, which we call a weighted displacement model. The way it works is for every point in the point cloud, we're predicting a residual, a delta XYZ, from that observation point to the target gripper location. Now, some of these residuals will be predicted more accurately than others, so we also learn per point weight, and then we take a weighted average to get the predicted location of the robot end effector. This has a nice kind of translation invariance property that if you move the object, the residuals should basically stay the same, which would result in the end effector kind of moving, like translating in the same manner. The low-level policy is fairly standard. We take in the observation and we input the predicted end effector subgoal, and after that, it's just a transformer diffusion policy. Okay, and so here, so now let's see how well that works. Here you can see the performance. You can see huge gains compared to the end-to-end policy, and it's actually able to generalize to the unseen objects when it's trained on enough object variations. So we end up with a single policy that we train in simulation, and we can deploy it on these 3 different robot embodiments in the real world with different kind of gripper types and things like that. And here you can see the deployment in our lab, another lab in South Korea, and various kitchens and lounges around our building. So you can see that it's able to open up all these different kinds of objects, dishwashers, fridges, microwaves, drawers, things like that. Yes.
Thanks, David. So this the ability to predict the robot pose, the robot end effector pose at the end of the motion, that seems to rely, particularly in these kinds of objects, on being able to judge the dimensions almost perfectly right. And it feels like it's kind of brittle to, if you say, okay, you know, if, for example, for the dishwasher, you judged its height to be just slightly different from what it actually is, that you would kind of end up with a pose that's very far off or something like this, right? Am I kind of intuiting this right?
A point cloud observation as input. We're not using images as input. So yeah, so the metric size of the object is directly part of the input. Yeah, does that address your concern?
So that mitigates the brittleness of being able to, of requiring that we are able to predict the final end effector pose. Just having the point cloud observation is basically sufficient for this?
Well, I guess it mitigates the concern you have about, you know, misestimating sort of the height of the object, because the height is, I guess, just directly part of the input itself. Now, yeah, the high level prediction could have some errors. And one of the ways that I think that brittleness is mitigated in our case is with the hierarchical structure. The high level is an input to the low level. So in theory, the low level could ignore the high level or adjust for errors in the high level. It's not, again, trained to reach the high level. It's trained to do the task, just with this extra input that is guiding it. Yeah. Cool, great questions. Feel free to jump in with other questions if people have. Every time step, we make a high level prediction. Yeah, and low level as well. Yeah. Yeah, so then that enables us to adapt to any changes that might have occurred, I guess, during the rollout. Yeah, you could imagine some kind of structure where you try to learn when the high level should make a new prediction, but we didn't want to add that complexity. We just said, let's just predict it every time step, make it easier. Here you can see the weights. So remember, our high level is this weighted displacement model where you take a weighted average of a bunch of residuals, and the weights are learned just end to end to predict the gripper pose. And you can see that the weights end up learning something very intuitive. So at the beginning, the subgoal is to grasp the handle. As you can see, the network ends up learning to put high weight at points that are near to the handle, because that makes it easier to predict the residuals correctly. After it grasps the handle, the next target pose is some location in the air where the robot would end up after it performed the opening action. And in that case, there's not maybe a particular point that's necessarily much more useful than other points, so the weights kind of become much more diffuse on the body of the object. So we didn't necessarily design it to have particular interpretability properties, but our network ended up producing these weights that are interpretable. So to kind of summarize, the approach that we ended up using that worked very well here is starting with large-scale demonstration generation and simulation, a hierarchical policy, and then that enables zero-shot real-world deployment and cross-embodiment. Now, I'd like to also tell you about some, yes, go ahead.
So, whether the high level, thank you. I was wondering whether the high level generalizes to different low levels, and whether it can compensate for possibly a poor low level policy. Say the high level has go at this position, but the low level always makes a 10 centimeter error in the position that it needs to get to. Will the high level learn to say, okay, that's a poor low level, I always have to say 10 centimeter more, or no? Or are they very tangled?
No. So let me kind of break that down in a bunch of different ways. So first of all, in practice, the high level is trained just to predict the gripper pose in the demonstration, and the low level is actually trained in the end. Yeah, so the high level, I guess, gets no feedback from the low level about what it should do. So it's not trained with like in an end-to-end kind of way. It's not trained with reinforcement learning. It's just trained to imitate the gripper pose in the demonstration. So it doesn't have any way of learning how to compensate for errors in the low level. Now the low level, you could imagine training in a couple of different ways. The way we trained it is we trained it with actually the ground truth as input to the low level. We've tried many times actually, because people keep suggesting this, to train it with the high level prediction as input. That seems like a really good idea, but every time we try, it leads to worse performance. I'm sure there's some way to get that to work and lead to better performance, but we haven't cracked that nut yet. So right now, the low level is just trained with the ground truth as input. Yeah, does that address your question? Good thought though. Yes. Yes.
Or something trained to match to achieve the particular end-effector goals?
Yes, yes. That we've done the experiment. It was asked for by reviewers, and we did it. Right. So the question is, could you just replace a low level with like a motion planner or something? It doesn't work for two reasons. So the first part of the task is to grasp the handle. So you have to. It's actually a little bit tricky. You have to kind of get like inside the handle. So there could be like if you use a collision-free motion planner, it probably wouldn't work because you might have to have some kind of small collisions with the object to get like inside the handle. So that's sort of the first part. The second part is even harder because if you imagine that you have to take a circular arc to open a rotational object, you can't just go directly to the final pose. You have to follow a certain trajectory. So a motion planner that's not learned wouldn't necessarily know what that trajectory is. Yeah, does that address your question? Yeah, great point. Cool. Any other questions at this point? Okay, so I'd also I'm really excited to tell you about some very recent follow-up work that we've done to this project that we call SMITH, which stands for Sim to Real Multitask Hierarchical Policy. The idea in SMITH is to take the project we just talked about and extend it to even more manipulation tasks. So previously we had opening. Now we also can close different objects, and also grasp things, and also place objects on top of or sometimes inside of other objects. So we generate a large-scale data set for each of these 4 tasks. Actually, to clarify that, for grasping, we just use the acronym data set in Contact GraspNet, but we generated data for each of the other 3 tasks. And again, trained a hierarchical policy on that same data. Yeah, this is a project, again, led by my student, Yufei, who's still on the faculty market, and an intern, Chen Yuan, who is also really good. So in this case, the high level, we had to design a little bit differently before we did a weighted average. But that weighted average leads to just one prediction, which isn't going to work for these more multimodal tasks like grasping a cluttered scene. So we modified the high level. In this case, we use something that I call a dense Gaussian mixture model. It works like this. So let's suppose you have your input is a point cloud with endpoints. And we have, let's say, training examples that are to grasp this object or to grasp this other object. And we want to output all the possible grasps for the scene. So our high level now is going to output a per point weight, just like before, except this weight will now be interpreted as the weight of our per point Gaussian in the Gaussian mixture model. And our low level, and we also predict a per point residual, except that those residuals are now interpreted as, if you add those residuals to the point, the location that you get is now interpreted as the mean of our per point Gaussian. So we end up with this Gaussian mixture model that has n Gaussians, where n is the number of points in your point cloud. So if your point cloud at 1,000 points, we have 1,000 Gaussians that we predict, 1 per point in the observation. And then we train it with a negative log likelihood loss standard for Gaussian mixture models, and it ends up predicting these gripper poses at all the different locations where you could grasp the object or whatever task that you're training it to do. We also tried using a diffusion model, which worked a little bit worse, but relatively similarly to this. I guess we chose the dense Gaussian mixture model because it has this nice equivariant property that if you move the object, the residuals move also, and it did give slightly better performance than the diffusion model. So here you can see the results. Again, this is just a very recent follow-up project that we did, but you can see the top row is opening these different articulated objects. The second row is closing different objects. The third row is grasping objects in clutter. And the fourth row is picking up objects and then placing them on top of other surfaces. I'll just go to the end here. Okay, so we've done some analysis to say how does this hierarchical approach compare to other approaches. So first we compare to, we do a comparison on these 4 different tasks of opening, closing, grasping, and pick and place. And we compare to Maniflow, which is just an end-to-end 3D diffusion policy, and Pi 0.5. And here's the performance. Although I'll note that I guess we're not experts in Pi 0.5, so I'd love to talk to you all to see what tricks you need to do to get it to work. But this is the performance that we got after talking to a couple of people who had some experience with Pi 0.5. And here's the performance of our method. And this was all on a droid robot and everything like that. So you can see that we have a huge improvement compared to Pi 0.5 and the other previous works, and especially on the tasks of opening and grasping that are particularly difficult. So you can see that we significantly outperform prior generalist models on these tasks. All of these, and then in comparison to, we also compared our method to state-of-the-art task-specific specialists. So we compared to the first project, Articubot, which was designed just for the task of opening, and also we compared to ConteGraphNet, which is a state-of-the-art method for grasping objects, and you can see our performance is almost the same. So, so even though we are able to perform these 4 different tasks, we are also able to match the level of state-of-the-art specialist models that are designed only for one particular task. Okay, so to kind of summarize here, our method, Smith, Sim-Trial Multitask Hierarchical Policy, is trained for these 4 different tasks in simulation with, in this case, it's 140,000 simulated demonstrations. We, again, use a hierarchical policy, although with a slightly different high level from before, and we again do zero-shot sim-trial transfer. Cool. Any questions, any other questions at this point? How did we, sorry.
The closing was a prompt, right?
Yes, we had a prompt for closing. What was the exact language prompt that we used? Oh, I don't know.
What did you use to interpret the prompt?
What did we use to interpret?
To transfer the language into like your task, because before you didn't show us any language interpretation, you showed us specific tasks, right?
Right.
The opening of the drawer was not a language,
right.
It was a task.
Right.
So how do you interpret the...
Sorry, for our method or for Pizer?
Your method.
Oh, for our method, sorry. For our method, yeah, we have a list of like 10 language prompts, so it's not very, I would not call this a vision language action model in any real sense. It has just 10 prompts that are like, open the fridge, open the microwave, open the drawer, close the fridge, close the microwave, close the drawer, grasp anything, pick up something, and put it on something else. Like those are, yeah, it's a list like roughly that long of very specific language prompts. Yeah, you can't give it an arbitrary language command and expect it to do something it will not. Yeah. Cool. Any other questions? Yeah. Well, that's a great question. So I would say it was definitely more specialist than say Pi 0.5, which can hypothetically do anything. But I would say it's more general than these other 2 methods. So ConteGraphNet you cannot use to open an articulated object. It's even if you trained it with some articulated object data, the way that the architecture is designed, it has no way of executing that task, basically. It's sort of designed just for the task of grasping, pretty much. Articubot, also the first project I talked about, could not be used for the task of, well, I guess actually it's sort of also not designed for multimodal, or tasks where there's multimodal outputs, because it does a weighted average. So it really is designed for a task where there's only one possible grasp for the scene. So basically, I guess the kind of claim is that these 2 policies have a particular design that cannot really be used in tasks beyond the ones that they were designed for, whereas our method has a design that can be used for more than just one task. We show it here on only one task. I have, I don't know how to do this, but here, I'll just do it. Yeah, so here's kind of an example of an even more late-breaking result of our method fine-tuned for the tasks of folding clothing. So basically, kind of show that at least our structure can be used for any task. So yeah, so I guess I don't necessarily want to claim that we have a generalist model. It's definitely not like super general, but more that we have a structure that can be used for many tasks that achieves the same performance as models that are designed for just one particular task. Right. Good point, though. Great. Yeah. Yes. 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 That's a great question. I have no idea the answer to that. Yeah, basically the only axis that we were pushing on here is, I guess, adding more objects within the scale or pose variations, camera viewpoints. So yeah, the number of objects for each of these tasks is quite large. It's 140,000 trajectories. But yeah, I don't really know what happens when you push it in the task dimension. Yeah, that's a great question. Cool. Any other questions? Yeah. Yeah, right. Of the keyframes. Yeah, that's a great point. I think that's one of the sort of like remaining sticking points of this project is how do you define keyframes for a very general task? For these tasks, it was easy. It was, I guess, the grasping, whatever frame you grasp an object, and then any frame that you open the gripper, and then the last frame in the demonstration. So, but not all tasks would that make sense? If you are pushing an object, then you might never open or close your gripper, but you might have a lot of motion with your gripper closed that is important to capture. So yeah, so I guess from Penn, there's I believe a bunch of work on keyframe selection like VIP and stuff like that, which I think could be good. We've tried some of those methods a little bit. We've also played with prompting Gemini to output keyframes and things like that. In my mind, it's still an unsolved question. So yeah, I think there's more work to think about with that. Yes.
You have an architecture that's working all for now.
Yeah.
Do you think you're seeing generalization across the task and that there's some shared information, either at the high level or low level? Maybe you saw this on the folding, like that comes to appreciating from the other.
Yeah. Currently, as best as I can tell, it's a bit closer to negative transfer, actually, which is sort of surprising to me. The tasks seem very similar. Grasping a handle, grasping an object on a table, picking up an object and putting it on a table. There's a lot of related things here. But you do get actually better performance from our model when you train it on only one task compared to training it on 4 tasks. So maybe that means our networks aren't big enough. The high level, to be honest, is just .++. We tried a whole bunch of other architectures. They all performed worse. I cannot tell you why, but that's what we observed. The low level is a modified version of DB3, which is also a very simple low level architecture. Yeah, we've tried a bunch of things for that as well. Nothing worked better. I'm sure there's a way to get positive transfer, but we have not achieved it. Yeah, that's a great question. So I guess what we have, I guess what we're hoping to see, and I guess we haven't fully demonstrated yet, but this is what we're hoping for a follow-up project is if you take this policy and then you fine-tune it on some downstream task like laundry manipulation, hopefully it will be better than just training from scratch. And if you were to pick one of these 4 for pre-training for laundry folding, I don't know exactly which one it would be. So kind of the hope is that it will be better pre-training for whatever downstream manipulation task you want compared to something else. But that's still an open question to be shown. Yeah, great question. Okay, cool. So I think I barely have enough time to talk about one more project now, so I will talk about this next project, which is how do we learn both generalizable and precise object placement? So this is a project led by my students Liu Xing and Eric. And for this task, we want to be able to do the two tasks that are shown on this slide. So and many other placement tasks. So on the left, we're showing an example from some of our lab's prior work on mug hanging, where we have to be able to generalize to all different kinds of shapes and sizes of mugs and different locations and poses of the mug rack. And so it has to have some amount of generalizability to be able to do that. On the right, we're demonstrating our method to perform this very precise industrial insertion task. This is the NIST task board, and it's a task that requires about a millimeter level precision. So how do we achieve both generalizability and precision for this object placement task? So we actually have kind of a series of projects in our lab exploring different ways of doing this object placement problem. The latest version is this. Basically, what we do is we take the point cloud of the object that we're manipulating and also the point cloud of the scene, and we input them into a point diffusion model. So this point diffusion model is going to diffuse the points of the point cloud in the goal location of where this object should be placed. And then we feed it to either a motion planner or a low-level policy, depending on the situation, to figure out how to move the object into that target location. Now, our initial attempts at this got kind of okay performance, but we found that there's a couple of tricks that you have to do to get this to work really well. So I kind of describe what those are next. So the first one is that we had to disentangle the shape of the object and the frame. So what I mean by that is we separately diffuse the shape of the object, meaning essentially you can think of this as like pose for the case of rigid objects. In an object-centric reference frame, we're diffusing basically the pose that the object should have in the placement location. And then we also diffuse the frame of the object, which is essentially the centroid, where the centroid of the object should be. And if you add these two things together, then you get basically the predicted location for every point in the point cloud back in the world reference frame. So that's kind of the first thing that we found led to much better performance. Yes. Yes. They are, I mean, they are sort of coupled in the sense that they're both being predicted by the same network. It's just that they're two separate outputs, basically. And yeah, you have separate decoders. And the other thing is that the combined output here is input back into the network. So the network sees the I guess the coupled representation where you see where the mug would be if you had these two things together. So that's an input in the diffusion process. We do not disentangle pose from shape. So when I say shape here, what I mean is the point cloud of the object we're placing in the placement pose in an object-centric frame. So there's no explicit rotation here. It's just the shape of the object, which you can sort of think of as pose in some sense. Yeah, great question. Okay, the other thing that we had to do to get this to work well, I think can be illustrated by this video. So this video is showing, so here you can see in orange all the different mug racks, and then in purple are the points that we're going to diffuse. So these are initially the noisy points of the mug that we want to place. And here you can see a video of them being diffused to the target placement location. Now, in this video, you might notice there's sort of two things going on at the same time. One is that the points have to move from their starting location over to the side of the scene where that mug rack is. So there's sort of like a scene scale diffusion going on. And then the points also have to diffuse into the right shape. So there's kind of an object scale diffusion going on. So the diffusion is kind of happening at these two different scales. And so even though we kind of, in the previous slide, showed that we decompose them, there was sort of an extra thing that we had to do to get this to work well, which is that we had to kind of initialize the frame diffusion to be a little bit more local. So the way that we did that is we have another network that before we run the diffusion, it predicts an initial guess as to where the mug should be placed. So in this case, we again use a dense Gaussian mixture model. So for every point in the point cloud, it's predicting this residual of where the centroid of the mug should be. And that is a rough guess. It's not super accurate, but that's our initialization for the frame diffusion that we then do later. Okay, so then in terms of results, here you can see for the NIST insertion task, we basically have the scene point cloud, which is the NIST board, the object point cloud, which is the plug that we are inserting, and we then diffuse the both the sort of shape of the plug and also the location of where the plug should go, and then here you can sort of see the combined diffusion like in the frame of the NIST board itself. And then our output is that we can then very precisely perform this insertion task. So we try this on the 3 different plugs in the NIST board. One is the waterproof connector, the D-sub connector, and the SSD connector. And you can see our success rates on each of these tasks ranging from 80 to 100%, even though these tasks require about 1 millimeter precision and around 1 degree of accuracy. These are just approximate numbers. And our method can also be used for these tasks that require some amount of generality, like hanging different kinds of mugs on different multi-peg racks, inserting different books very precisely into a bookshelf between, I guess, sort of like you think of it like between other books, or placing a can in a specific location in a cabinet. And you can see you can also, since this is a diffusion model, you can run it multiple times and get different types of placements. You can also, since we're diffusing a point cloud and not an SE3 pose, you can do this for a non-rigid object. This is, I guess, not a particularly deformable object, but it's one that we were able to get working quickly for the demo for this project, which was diffusing this cloth that has a hole on it, and we're trying to hang it on this rack, and it deforms at least a little bit over the course of this manipulation task. So here you can see some quantitative metrics for the 3 tasks in simulation on the placing the mug in the rack, the book in the bookshelf, and the can in the cabinet. You can see the error rate of the initial version of our method, a prior work that does SE3 diffusion, and our final method. Now, looking at this result was actually a bit surprising to us. This method here is SE3 pose diffusion. It's a prior published work that's very good and inspiring to us. And here is our method that does point cloud diffusion. And this should lead you to ask a question. These 3 tasks here are rigid object insertion tasks. So why is it that you can't just do SE3 pose diffusion? Why do you get a benefit for diffusing the points in the point cloud? And so to understand that, we did an extra analysis, which is we tried training and testing the models just on 1 mug versus training and testing them on many mugs. And so if you train and test them just on 1 mug, then the performance difference between our method and SE3 diffusion is very small. Both methods pretty much work. If you train and test them on diverse mugs, then you can see there's actually a huge benefit from point cloud diffusion compared to SE3 diffusion. And to help explain why this is, so I guess the intuition here is that I think SE3 is basically harder to generalize across object shapes. And so to explain the intuition behind that, I'm going to steal these slides from this other paper called Neural descriptor fields. Anthony Simonov, gracefully shared these slides with me that he used in his PhD defense. You can see here an example where we are trying to grasp this picture. And if you have the same object in training and test, then you could basically just estimate where the grasp is relative to some reference frame on the object, and then transform it to this other picture. But what happens if the picture shape changes? If you try to transform the grasp based on this object-centric reference frame, then the grasp fails because essentially the picture is much smaller. Now, you could fix this by defining a reference frame that's on the lip of the object, and now if you try to transfer it, then your grasp will succeed. But that reference frame is task specific, so if you had a different task, which is placing the picture on a table, now you want your reference frame defined relative to the base of the object, and then you'd have to transfer that. So essentially, if you want to try to do things in SE3 pose, you often need to define a task-specific reference frame to make the pose be able to transfer to objects of different shapes. Whereas if we do point cloud diffusion, the point cloud diffusion model can, I think, more easily learn a task-specific reference frame just from the demonstrations that generalizes across different object shapes. Great question. So if it's the case where we're doing motion planning, then we use SVD and ransack to compute the pose. Yeah, so we still go back to classical methods at the end, but we're diffusing the point cloud with our network. Yeah, great question. Cool. So to summarize this, we are learning both generalizable and precise object placement via point cloud diffusion, and we demonstrate on both tasks that require some generality, mug hanging, and these tasks that require very high precision. Just to check, I'm supposed to end at 11:30. Is that correct? Sure. Yeah. Okay. Yeah. Okay. Yeah, I do not really think I will have time for this third project, but just to kind of show you, this is another project that on planning from point clouds over continuous actions. We're trying to explore how to combine learning and planning together, where we want to plan in a visual space. And so the basic idea here is this going to work? A spinning wheel. The basic idea here is that we want to do a search over a sequence of object placements. And so if you remember the project I just presented, we are diffusing object placements. And you could imagine a method that diffuses a sequence of object placements, that searches over a sequence of object placements. So you can have output multimodal placement options, and then do a search to figure out which placement option is the best. Okay, this just froze. I think I will kill it and restart. Okay. Yeah, so just to kind of show that, so this is the task that we do, which is it's called table busing. You're supposed to stack all the plates and cups and bowls first. Sometimes you start off with like a cup that's somewhere that you have to take off before you can stack the other things. So you kind of have to reason about the sequence of placement tasks that you do. And yeah, I guess we significantly outperform just end-to-end policies on this approach. And I guess we perform maybe comparably to some other planning methods that operate in a symbolic space, except our method doesn't reason in a symbolic space kind of in that same way. Okay, cool. So just in the interest of time, I'm going to jump to the end, which is here. So I guess there's this question about how do we obtain both precise and generalizable robot learning. So in the first project, I talked about manipulating articulated objects, and we see, and also the follow-up work Smith that has more tasks. And we can see the idea of hierarchical policy where the high level predicts a grip or subgoal, and the low level predicts robot motion. The second project that I talked about was about precise insertion. And here the high level is predicting the object placement very precisely. And the low level is either a motion planner or a learned policy that can predict how to reach that subgoal. The third project, which I didn't have time to talk about, was about learning and planning, in which we're searching over a sequence of high-level placements. So I guess the running theme here is this hierarchical motion policy, where at the high level we're reasoning about some high-level motion, and the low level we're reasoning about low-level motion, and they're both learned. You can combine them to achieve both precision and generality. Some future things I'm interested in are reasoning about object interaction and tool use. So if you have a robot that's to perform some tasks, it requires it using different tools in some sequential order. I think it would be interesting to enable robots to be able to reason about how to do these tool use tasks. And I think there's also much more to explore in the learning and planning direction. So I'd like to acknowledge the fabulous students and postdocs who I've had the pleasure of working with over these years, and also my various funding sources. And I can end here and take any remaining questions that people have.
Thank you very much, David, for a very inspiring talk. Let me maybe kickstart the questions at the end by asking something that's been kind of riding on my mind throughout, which is that when you have this kind of modular structure to your policy, it feels like one of the advantages you could have is that these modules could be potentially drawing from different data sources, and therefore you kind of in line with our conversation yesterday, you could say, for example, that the high-level module, the high-level, the high-level policy could here be drawing from different data. It could be trained on more data or something like that.
Yeah.
But that hasn't really been the argument, I think, in your line of work.
Yeah.
So maybe kind of broadly your comment on that. Is there a reason to believe that just having the structure is already, it feels like that's kind of the argument you're making, that having the structure is already really helpful.
Yeah.
It's just kind of almost like an inference time trick that you kind of, keep this kind of high-level motion as a kind of grounding factor for your low-level policy. And do you think that you might even get better, better improvements by exploiting other data?
Yeah, that's a great question, and it's something we're thinking about. I guess you're already thinking 2 or 3 papers ahead for us. But I guess my intuition about it is that because it's a hierarchy, I think the high level can be trained on sort of noisier data than the low level. I think the low level needs very precise data because it's the one outputting the robot actions at the end of the day. But the low level is just providing guidance. So I think the high level actually could be trained on more like web scale data, internet videos, things like that. And if it's not perfect, that's sort of okay. It's just providing some guidance. So, yeah, I think your point is spot on, personally.
Thank you. Questions? We had a lot of questions before, but I'm sure we have more.
So I love the talk, David.
Thanks.
I feel like I don't understand why the high level guidance is helping, and I don't know if you've gotten any insight as to like what exactly it's doing, particularly because the low level policy is not trained to mimic it, right? It's just the behavior cloning loss.
Right.
It seems like a smart idea. It seems like it's working. Yeah. Why? I guess.
Yeah. I wish I knew, actually. I mean, yeah. So from the one standpoint, it was an empirical finding. We tried lots of things, and this was the only thing that worked. That we tried. I guess if I had to kind of give some like vague intuition about it, I guess the high level architecture is kind of designed to reason about the scene kind of globally and understand. I guess it's sort of forced to understand the parts of objects and things like that. And the low level, I guess, both the training data and the structure of it, I think is more appropriate for like continuous motions, I guess. Yeah, that's the intuition I
One
have.
one hypothesis might be that the high level guidance is particularly useful when you're far from the grasp, and then it kind of transitions to the point cloud.
Yeah.
I don't know if you've got any evidence to that
Yeah.
or believe it, but
I think that's right. Okay, yeah. But now that I guess you're phrasing in that way, I suppose we could do an experiment where we try the end-to-end train policies, but just initialize them kind of like close to the grasp or something like that, and see how good it can do at grasping, things like that. Yeah, that would be a good experiment to try. Yeah, good point.
I also found very interesting the kind of the choices that you made for, I think, the action space for the high level policy. It felt like even on this slide, we can kind of see that the high level policy, in the first case, I really like this kind of like Huff voting style, like every point votes for where the final gripper is supposed to be.
Yeah.
Can you tell us a little bit about what those choices, why those choices were the most natural, or were they kind of, through careful design? It feels to me like, for example, that Huff voting style thing, again, drawing lessons from computer vision, it feels like the kind of thing that's likely to be robust to like some missed points in the sim to real transfer. Is that the real benefit of it? Like, have you done some analysis to see what it actually helps with?
Yeah, that's a great question. So yeah, in terms of the high level design, I guess the two pieces are, a per point weight and a residual, and then either doing a weighted average or a negative likelihood loss, thinking about like a mixture of Gaussians. Yeah, and so I guess my intuition for the residual is generally that I think small, I guess my kind of intuition, I don't know if people agree with this, is that kind of like small residuals are a lot easier to predict. If you're doing a regression task, it's kind of easier to predict like a small delta than an arbitrary length vector from in a generic world scene coordinate system. If you're doing world scene coordinate predictions, and instead of relative to some arbitrarily defined reference point, where should the gripper go? And that's somewhat arbitrary. Whereas predicting that a gripper should be, a centimeter away from a handle is sort of a very consistent prediction, has a strong meaning that's tied to the object. It's translation invariant. If you move the handle, it should still be a centimeter away from it. And I think it's much more grounded and easier for a network to learn those residuals than just a generic pose in an arbitrary frame. And then the weights kind of make sense in that tied with that if you're predicting, where the gripper should go relative to something, well, it shouldn't be relative to some distractor object. It should be relative to the thing it's manipulating, basically. And so that's I guess what the weights hopefully would learn, and do seem to learn that. Yeah, I guess the other choice we made is predicting 4 gripper poses, which I guess sort of just ties into this residual idea. You could predict a rotation, but the rotation isn't, I guess, in like what's your reference frame of the rotation? What's 0 degrees mean? It's a little bit arbitrary, whereas the 4 points are again all just residuals. Yeah, that's a great question.
Yeah, thank you.
I really liked your work on RTQbot, and it was really cool that you use like simulation samples for zero-shot real-to-sim transfer. A question I had was that I've seen some of your work on Gaussian splatting as well, where you're like using better RGB rendering.
Yeah.
So if you were to continue on this line of work, what is the next step for simulation? And are you taking a look at stuff like, for instance, real-to-sim, where you import like where you digitize real-world assets, and maybe perhaps think about how they can be articulated better, or they can you can import their actual physical properties such as friction and stiffness and all those other physical properties for improved sim to real transfer?
Yeah, that's a great question. So I have a number of thoughts about that. So one is that I might point you to a different prior work from our group called RoboGen. The last author of that is Chuang Gan from UMass Amherst. And the idea is as follows. If you're trying to do sim to real, how do you scale it up? How do you generate lots of different simulation with different tasks and objects and things like that? And if you think about simulation is actually just code, and LLMs can write code. So what we do is, in that paper, we use LLMs to basically write the code for many different simulation environments with all different setups and tasks and things like that. And then you can kind of scale that up. The real to sim direction, I think, has very different use cases. I think it's really hard to scale up real to sim. You'd have to scan a lot of real world things to get to the scale that where it kind of can really make an impact. And I think it's also limited in the sense that there are things that simulators just can't simulate, like cracking an egg, peeling a banana. At some point, you really just have to combine sim data with real data. And I guess I think, yeah, so that's kind of my opinion on that. Yeah, great question though. Yeah.
Thanks for the great talk, Dave. I was curious, so it seems like sim to real is like a big paradigm for your lab.
Yeah.
And what kind of helps enable that is you're using point clouds for a lot of the policy inputs.
Yeah.
And I'm just curious how you deal with the sim to real gap in the point cloud noise. Like, are you just modeling that in sim well, like this sensor noise that you expect to see in real? Or are you getting lucky with how you compute like kind of attention weights in for each of the points that it's like robust to this gap?
Yeah, that's a good question. We don't really do a lot with that. I actually, to be honest, I don't fully remember. There might be some small amount of like Gaussian noise applied to points or point dropout or things like that. But I guess my feeling is that, you know, we do randomize the camera pose, so that effectively creates random object occlusions. But we don't have to put a lot of effort into getting sim to real to work in point cloud space. I think in RGB space, it's much harder. You have to put a lot more effort there to get sim to real to happen. But in point cloud space, it was pretty natural. Yeah.
Is it okay if I ask one more follow-up question? So this is a different question, but I'm curious. A lot of the tasks you've been tackling today are very like geometric and kinematic. And I'm wondering, once you move to more like dynamic tasks, do you think there's another level of abstraction that you need to start moving towards? Or do you think this same like just two-level hierarchy will work out?
Yeah, that's a great question. I do think that there's another level that you would probably need. A couple of papers I really like about that. One is, I believe it's called RK Diffuser, and the other is Shuron's recent paper, maybe it's called HUMI, H-U-M-I, humanoid UMI, where they have a hierarchy. Both those papers, I guess they actually solve it in different ways, but I guess below the idea of predicting end-effector poses, you also maybe want to predict joint angles, especially when you have something very dynamic, relying on a position controller to reach the end-effector poses at the precise times you need for a dynamic task might not always work out. But if you are predicting joint angles, then you're kind of controlling the pace of the robot that might be more appropriate for very dynamic tasks. Yeah, that's kind of my thought on that.
Thank you.
Good question.
Good question. Well, if not, then thank you all once again for being at the seminar. And thank you, David, for a really inspiring talk.